So now we find
Okay,
ourselves
great.
with
Thanks,
these what we're
Rob. As
calling
always,
third
extremely
generation
knowledgeable
bits,
presentation.
clocks,
Next
sync
up is
systems.
Microchip's Jim Olsen. If you've had the pleasure of working with Jim in the past, I'm sure you know that he is truly an expert in the field. Take it away, Jim.
Hello, everyone. So I'm Jim Olsen, Solutions Architect for Microchip. I'm going to talk today about two things. One, an enhanced primary reference time clock, and the other one is a virtual primary reference time clock. They're two different things, and I'm going to try to help explain what they are and what the differences are. So an enhanced primary reference time clock is referred to as an ePRTC. That is an industry standard from the ITU, and it's a timing system. It consists of different components of the system, one being a firewall that detects GNSS or GPS anomalies and forces the system to switch to another reference. It also consists of a GNSS timing receiver that has ePRTC algorithms in the receiver itself. This is an example of our product, the TP4100, that Scott described as an ePRTC configuration. The third component of the system is the cesium atomic clock. The cesium atomic clock is required to meet the performance specifications of the system. We'll talk about what those specifications are in a few minutes. The virtual PRTC is not an ITU standard, it is a concept. And the concept is that we want to deliver or create a PRTC function within 100 nanoseconds to UTC at some drop point in the network, typically an aggregation point, where no GNSS is going to be required. The components of a virtual PRTC is at least one, but typically two ePRTC systems for source clocking. It also needs an optical or OTN network to deliver the timing from the ePRTC location to the virtual PRTC location. We do that by using time transfer with PTP from the ePRTC to the virtual PRTC. So in this case, our source clock, the ePRTC, will track within 30 nanoseconds of UTC traceability. That allows us to create some level of time error when we do time transfer over the network and still meet the PRTC requirements of 100 nanoseconds to UTC at the virtual PRTC location. An enhanced primary reference time clock based on the ITU standards must track within 30 nanoseconds of UTC. Typically, these systems are probably around 15 nanoseconds or maybe better to UTC on a consistent basis. If GNSS or GPS becomes compromised and is no longer available, this ePRTC system must hold 100 nanoseconds for at least 14 days. This is a specification that is a requirement, 100 nanoseconds for 14 days, meaning it must still meet the PRTC-A requirement of 100 nanoseconds to UTC after 14 days with no GPS available any longer. From tests and deployments in laboratories and networks, sometimes we see 60 to 90 days with the system without running with GNSS or GPS after it has been removed, for 60 to 90 days to 100 nanoseconds. So this is phenomenal technology. And if you're kind of a nerdy guy and you like technology, this is in that class of really cool technology. We have a couple ePRTC use cases. We can use it as a virtual primary reference clock, which I'm going to talk about in a few minutes, where we do try to set time within 100 nanoseconds to UTC at a location to create a PRTC function. We can also use it for assisted partial timing support, or APTS. APTS is used to hold time or create a GPS or GNSS proxy at a PRTC location. At some point in the future, we'll probably do additional presentations, and we'll probably cover this topic of APTS or assisted partial timing support at that point. A primary reference time clock is a function. It is the ITU standard G.8272. So a PRTC can be a system. It can be a GNSS and GPS timing receiver that also has PTP server capability built into the product. But it can also be a network. G.8272 specifies the time error at the PTP output relative to UTC for different PRTC statements. PRTC-A and PRTC-B. PRTC-A is better than 100 nanoseconds to UTC, where PRTC-B is 40 nanoseconds or better. With our product, the TP4100, we can configure it as a PRTC-B. Typically, to consistently meet that performance level, we have to do what Scott was referring to earlier, using multi-band or multi-constellation antenna concepts. A virtual PRTC is a transport network that uses PTP time transfer to deliver precise timing services. We try to create a PRTC-A function at any desired location in the network by transporting clock from the ePRTC locations to the virtual PRTC drop point in the network. We can use different types of transport technology to create a virtual primary reference time clock. We can do Ethernet with boundary clocks in it with class C or better. We can also have an optical layer with standalone high-performance boundary clocks. An example of a high-performance boundary clock is the TP4100. We also can do optical layer with class C or better that's embedded in things like ROADMs or other types of optical transport technologies. A virtual PRTC is a system and a concept for time transfer over the network that is very resilient. The reason we get resiliency with no single point of failure is because we can do bidirectional PTP timing flows over the network from two locations, from a west location, for example, or an east location. If we had a mesh network, we could actually have 3 ePRTC functions and do tri-directional timing flows. But for example, in a bidirectional PTP timing flow scenario, we can send timing from the west ePRTC and the east PRTC with PTP flows over the network and create a drop point in the network through high-performance boundary clock functions with a southbound PTP interface that meets the PRTC 100 nanoseconds to UTC traceability specifications. In this illustration, we show bidirectional timing flows. So if we have a fiber cut in one direction, we can continue to have timing flowing from the other direction as well as traffic. So we have a highly redundant, highly accurate, highly resilient way of delivering accurate timing and creating PRTC functionality at drop points in the network anywhere we desire. This illustration shows some examples of how to do optical timing methodologies. We can do timing in band over optical networks such as DWDM or ROADM products. If we look at number 2, we can also do timing over DWDM networks using external high-performance boundary clock functions. In many cases, the optical equipment in the networks does not support embedded timing. So in this case, we would send the timing around the DWDM muxes through a high-performance boundary clock that could be the time provider 4100 to create our virtual PRTC function at the other end of the optical network. We could also do a hybrid sync solution that part of it is a virtual PRTC with external high-performance boundary clock functions, where part of the network may have embedded boundary clock functions, creating a hybrid environment for sync distribution. So in conclusion, a virtual PRTC with high-performance boundary clock attributes creates a stable, predictable transport for timing. It has to be a fast transport network. It cannot be necessarily older technology involved without using external high-performance boundary clock functions. We can deliver very deterministic time error with very fast protection. The TP4100 has built-in capabilities, for example, as an external high-performance boundary clock to take measurements and look at messages to switch references, for example, from an East PRTC to a West PRTC. This architecture is immune to GNSS problems such as interference or a loss of signal due to some sort of failure. So that is related to the ePRTC function that relies on the cesium atomic clock for enhanced holdover capability. So this is a controlled, managed, monitored PRTC network where we don't use GNSS at aggregations or edge points in the network. This allows operators to save money and create a redundant configuration that delivers accurate timing. So there's cost savings involved, and it delivers a timing network without single points of failure. So I hope this helps everybody get a little bit educated on enhanced primary reference time clock as a system function and virtual primary reference time clocks as a network to transfer time.
and thank you all for attending today's What's New, What's Next webinar. We're happy to continue the conversation via phone or email. Please reach out to us. And thanks again until next time.